Hello, welcome. Apparently, I'm not Edo Karl, who was supposed to give this talk. He can't be here. He can't travel at the moment. So the decision was made that I would step in and give this talk. My name is Andreas Otte, and I'm a member of the SAM team. Okay, introduction. At ICCF 25, David Nagel gave a talk about, let's get this right, surprising correlation between peaks in LENR transmutation data and deuterium fusion screening data. Based on the structured atom model, SAM in short, the team has attempted an explanation for the nature of those peaks. I hope it satisfies David. We'll see. So, part one. Basics of SAM. I'm not going into basics of SAM. I assume that you have either read the book or have been part and seen some of the presentations over the last few years. If you have questions on that, then ask me later. Basically, it's one thing that I have to say, is that it's a geometric model, and it has a fixed structure for each element in the nucleus. So this one you have seen before. This is a video clip that goes through all the elements and isotopes that we've constructed based on the rules of the model. And as you can see, it is basically going through the structure, and you see that it elongates and that it branches out. That is very important. So we have apparently what I would call a backbone inside the nucleus, and this is, as you've seen, this grows basically, and we have active endings on the ending of the branches. So it is made up of icosahedron structures, this backbone. The initial one consists of 12 protons and 6 inner electrons, or 6 deuterons, no neutrons. So we consider the neutron to be a pair of an electron and a proton, very old concept, but that is part of the model. So it is there, but it is not on the same level as a proton. It's not as a primary particle. So as I said, 12 protons, 6 inner electrons, or 6 deuterons. When we connect another icosahedron to that, it provides only 11 protons and 5 inner electrons. So we have something that we call a PEP, a shared PEP. That is actually what we would call a neutron. And it is basically the connection between the two icosahedrons. This fractal geometry that is created is a little bit complicated. It has an angle of 31.5 degrees. And that initially, and that is because of a top gap that is created on the first icosahedron. When we move from carbon to nitrogen, basically it rips off the structure. And then, of course, it is tilted and rotated by 36 degrees. That is what you would expect for an ideal structure, but this is not an ideal structure. So and that has obviously consequences when it grows. So this is another view. This is a view of the backside, basically. And as you can see, it first elongates and then it branches out. This is based on noble gases and similar structures. Just to visualize this further, what is going on when the nucleus grows and when we go from element to element. So second part. So what are the SAM specifics related to the discussed talk or paper? So we talk about what we call Sollbruchstellen. This is me doing that. It's in English, it's predetermined breaking points, but that name I used stuck, so we kept with it. It's one of those typical German words that comprise something in one word. Then we ask the question, of course, what is the process? And what pieces do we expect to see if a nucleus breaks up? Yes, fission. And we look at an example breakup of palladium. So what are those Sollbruchstellen of the nucleus? And those are basically those connection points between the icosahedrons. This PEP that is the connection point. The icosahedron itself is a very strong substructure, so it will break at the connection points. When we have even if you have very small nuclei, such shared PEPs or neutrons already exist. It starts once we call it the building phase starts. And so the first one where we see this is actually sodium-23. This red part is basically six nucleons, and then a seventh that is shared with the icosahedron. But this is the first one that has that. So this icosahedron has basically two of those connecting points. Here we see magnesium, and so we have two of those shared PEPs. And what we also can see here in the middle is the gap. This is what I mentioned before. When we first start and put a deuteron on top of this icosahedron structure, which is carbon, so we go from carbon to nitrogen, it rips off the structure a little bit. And this gives us this strange angle of 31.5 degrees, and it determines basically how the nucleus, in which direction it will go. When we further look into what are the endings, this one here, like magnesium, is a little bit atypical. Mostly what we see is what we call carbon endings and oxygen endings. So they look like carbon if it would be on its own, or they look like oxygen would be on their own, but they're connected to the structure. So those are the active endings. And by the way, the chemical structure or the chemical behavior of an atom is, we think, based on those endings, which in turn have effect on the electrons. Okay, so if the nucleus grows, once it starts to have branches, which is around iron, nickel, those breakup points will become important. This is a small example, easy one. I don't think this will happen actually, but it's just to show what is going on. We have silicon-29, and for whatever reason, the carbon basically is disconnecting, and what is left basically is an oxygen-17 and a carbon-12. But this shows what basically happens. This is a breakup point. Not that it would really do this in this kind of configuration, but it clearly shows what is going on. So what is the process, what we think about what is going on here? The first step is the delivery of a proton or a deuteron to the nucleus. How this happens is, we are under discussion. Let's say when the Blasen theory has some ideas, then of course we heard about electron screening. We call it proton capture. Whatever the real thing is, we need to have some new protons into the nucleus to make it grow, to have a fusion basically. So we call this process FIF in short. This is fusion-induced fission. And this part here of the process is basically the first part, the fusion process. So we add something to the nucleus, and then it might be done or something might happen. So this nucleus, resulting nucleus, might be stable or might be unstable. In case of a stable element, it is basically an instant transmutation. Nothing is going on, it just changes. In a case of an instability, it might be just a small change. It might be a better plus decay. It falls back to the original element, but with a different, basically a different isotopic number. But if it is the change is this, there's more instability, those Sollbruchstellen will come into effect, and it will rip basically the nucleus apart. And this is the fission part of FIF. So if you look at this, so we start with palladium-106. And as you see here with the circle, there is a PEP readily waiting for a proton. It comes in, it connects, it creates a deuteron, and we end up simply with the structure of silver. It can be that simple. It's instantaneous, and there is nothing more going on. No strange radiation, nothing. So if we have a minor change, then it could be something like this. We start with palladium-105. We add the next proton, but the configuration on top of it is not allowed. There are certain rules in the model, and this configuration that we have there is not allowed. And so it collects an electron, basically, and becomes a new PEP and is located a little bit on this ending. This, by the way, what we have there at the, is happening the same way with fluorine. So you have an oxygen 17 and add something, a proton, to it. You would get fluorine 18, and that is not stable, and then it falls back to oxygen 18. And as this ending is just like fluorine, this is exactly the same thing that is happening there in the model. So we end up with an isotopic shift. So what do we see if the nucleus really breaks up? Then we see something, would say, with smaller nuclei, something of a peel-off effect. So it would start to rip off endings around the nucleus. And those would predominantly be, from our point of view, oxygen and carbon. Those are the most likely ones. That's simply, when we go through the model, that's what we mostly see, oxygen and carbon endings. If we have heavier elements with big branches, then what we see is that basically branches are ripped off at those Sollbruchstellen. And this is very similar to what we already showed before, so I just have a small picture in here that is basically uranium fission triggered by a PEP or a neutron coming in, making the whole thing unstable, and then the branches break off. This is a model, but it is the only model I know that can predict the exact numbers of the breakup of uranium. So if you know of anyone else, of anybody else's model, please let me know. I would like to know that. So in case now we have the breakup of palladium-106. So what we see here is basically that it's a different isotope version. It comes in, it creates this lithium ending. It's the red one. That's what it's called in the model. And that, again, is not an allowed basically configuration. It's forbidden. So the nucleus reacts and tries to get rid of it. And in the end, we end up with a carbon-12, basically, and what is left on the nucleus, again, is what we call 5 ending. That itself would be allowed. But now the thing is too elongated. And that is also why, for example, it is still unstable, like technetium. By the way, in the model, technetium also is one of the most elongated elements, and it is basically the reason that it is unstable, and now it can't grow longer. It has to basically create branches. That's what's happening. And here, what it means is it has to get shorter. It doesn't have any more material. It can't do that. So it just has to get shorter. So what we think happens is that we shed 2 oxygen endings here. So we already got rid of 1 carbon, and now we get rid of 2 oxygens, basically, on this nucleus. And what we end up, basically, is more or less copper-63, minus some chirality issues. But it is basically the same structure that we see here. So, and the oxygens, basically the oxygen 17 first, or oxygen 16, have a little bit of remodeling, and then it is also okay. So, so in essence, what we expect to see is oxygen and carbon as main products of being ripped off the nucleus, and the remaining bigger part, which in this case looks very much like copper in the model. We think that this can also work the way around. We think there are fusion steps possible with carbon and oxygen. I remind you of the experiments from Slobodan Stankovic, which at least showed that carbon fusion seems to be possible. And it is this COO, or CO2, 44 nucleon step that we think is also visible in abundance charts on Earth. So it could very well be that maybe the heavy elements are not created in neutron stars, but they were created in a heavy electrical environment on Earth in situ. And we see those peaks because this is those carbon, oxygen steps are the preferred steps. So, and of course, what I talked here about is cold fission, if you want to say it like this. We have a fission, and this is one of the basically a quote from a book called Fusion Travelogue by Akito Takahashi, which himself quotes somebody who's called Yosha, and he basically he said that I was concerned about the report that the produced elements showed a distribution similar to that of nuclear fission. It is believed that light elements other than uranium and plutonium do not undergo nuclear fission. Is this really the case? And I think that we have seen now so many experiments, reproducible elements, experiments that show lighter elements popping up in certain steps that I think we have to accept that there is fission happening in those experiments. Or as I would say, if it looks like a duck, if it walks like a duck, if it quacks like a duck, it just may be a duck. So, part 3. Now we come to actually the paper. So the paper talks about 3 groups of experiments with diverging setups, and the transmutation data in there is compared to Willem-Larsen theory. But we ignore Willem-Larsen theory here, and we just focus on the transmutation results. The data is also compared to screening data. We ignore that too. But what we want to look at is the common metals in those experiments. And that, at least from my analysis, seem to be platinum, palladium, nickel, titanium. Those were the metals involved in the experimental setup. And this here, of course, then is some chart of the talk. I think it comes from Storm's paper from 2010, and it was slightly modified. David put in those dotted lines, vertical lines, which he also had on the one of the first slides I had in this introduction, and those were basically the peak points from Willem-Larsen, and also from the electron screening data. And here we see those peaks around platinum. We see it also very prominently around copper. So what we think happens, all those elements, those metallic elements in those experiments are basically subject to this process that we might have a little bit of a fusion process, which might be stable. So that's when you get from palladium to silver or from platinum to gold. It might be even one or two steps further. And if that doesn't make it, it falls back to the original element, but with isotopic changes. And if it's still unstable, then it will break up, and we will see those steps. And I think I made clear here that there is a path in the model that goes from, at least from palladium to copper. And we have smaller parts like oxygen and carbon. That Storms here doesn't display those, but in the other charts, oxygen and carbon was visible. I think Kumar also saw that in his experiments. This basically, I think this fifth process, fusion-induced fission, is one of the main reasons we see those peaks here around copper and zinc. And that basically would be our explanation of the peaks and why it happens, and that is basically based on the model, how the endings are and what is being shaved off in case of instability. Okay, I think I said that all. Thank you very much.
Thank you. It's open to questions, but I am holding the mic, so I have the first question.
Okay.
I like this work. I've done experiments, maybe you've seen it with a laser beam on palladium, and I found a lot of oxygen, as you have shown, carbon, and also I found a lot of nitrogen. Can you explain nitrogen? Because it is abnormal to have nitrogen in the metal, somewhere it's a gas, you know. So I want to give you that for thinking.
Okay, at the moment I'm not aware of because of course there's a nitrogen ending. As something, just the carbon with one deuteron extra on it, that's nitrogen. And out of my head, I don't think there's a nitrogen ending on palladium. But let me check that if I can identify that.
Okay, thank you very much. Okay, and there's a question. Who has a mic? Where's the mic? Where's the mic? Nobody's called Mike here.
I don't always need a microphone. I got one of those voices.
Yeah, but the people that are online do not hear you. So, do you have another microphone? Oh, on the table. We have two. Hopefully they work. Does it work? It does work.
Thank you. In your model, you talk about the PEP, which I've also seen described elsewhere as a pseudo-neutron. Yeah,
it is a proton-electron pair. But it is a proton-electron pair. It represents a neutron. We just don't think that the neutron in the model, or that the neutron actually is a primary particle. It is a combination.
Right. Okay. That you've answered my question. I think I wondered whether you recognise the existence of real neutrons, kosher neutrons, if you like, and PEPs, yeah.
Yeah, that's basically the replacement. It's just that it is not a primary particle in our view, so we set up the nucleus with protons and inner electrons. And of course, there could be this combination of one proton and one electron, which would be called a free neutron. And but we don't like the name neutron.
Okay. So, but what you're saying is that there are no neutrons; they're all PEPs. Okay.
Yes.
Okay.
So that's always this combination.
Yes, sure.
And I mean, what happens is, after 10 to 15 minutes, do you know what happens to a neutron?
Oh yes.
Yes. It disintegrates into a proton and an electron. Why?
Yeah. Very good point.
Maybe it was like that.
Yeah, sure. So in some ways you made things simpler, in other ways more complicated.
Could be, yes.
Thank you.
Thank you. I do like this work. Have you considered that any product that would come out of a reaction that yields net energy has to occupy smaller amounts of distortion of the physical vacuum than the originating product? So i.e. if it's squeezed into a small box, it's alpha and alpha conjugate nuclei, which would include things like carbon and oxygen, and calcium. And so, have you
we have in the experiments we have seen those cavities. We have seen a lot of strange effects, small explosions. So whatever is happening there, apparently it happens very localized, but then with huge amounts of energy. And so this really, it is.
So I'm looking at page 127 of the freely made available Steps to the Discovery of Electronuclear Collapse, paper 1991. And in your thing, your structured atomic model, you said copper and other elements are typical. And in his focused zones of reaction, you see copper production from palladium deuterium in a sodium chloride electrolysis.
What the model says would happen.
Yeah, so it's very interesting. So thank you very much.
Thank you. Next question. Yeah.
Thank you very much for the talk. I just had so like when Jean-Paul mentioned nitrogen, were you basically suggesting that the deuteron could fuse with some of these heavy nuclei? Was that, or am I misunderstanding?
Yeah, I mean, what we see is that when we progress through the nuclei, it's always like we step through it. You have a proton and a PEP, or just a deuteron, and it attaches basically to that existing structure at a certain place, and that gives you the new element. And so there are basically rules for where those attachments are allowed in the model, and so this is the way we progress through basically the periodic table of elements. So
right. So
this is basically what is happening there. And the colors, don't be distracted of the colors. This is just to show certain structures. Those are all protons.
Okay, but so, I mean, the calculating DD fusion rates, for example, let's just say, to be observable is already quite a challenge. But if you're taking a heavy nucleus like palladium or something, I mean, the Coulomb repulsions, the most surprising result. Okay. The most surprising results in all of the LENR literature are probably Iwamura's transmutation results, which are pretty incredible. But to explain, the addition of a deuteron to a heavy, a nucleus with many protons seems, I mean, insurmountably difficult. No.
Yeah, I mean, we don't do those calculations yet. The model is very visual. We think this is what happens in the model. And of course, what we then do is that we try to compare the model with reality and what goes on. We don't do those calculations yet. If you feel free, if you want to do those, be my guest.
It's not for me to do, though, right? It's for you to do. But I mean, there's very well defined fields like nuclear cluster physics, shell model calculations, which which explain many dynamics for nuclear structures. But those would be those would be the calculations to do for a model such as this.
Okay, I think we should stop here. Another question. Can you pass the mic here?
Hi, great talk. I was not familiar with the model, but I just bought the Kindle and will be reading it soon.
I have even 2 books there if you
I would love
wants
that.
them.
I bought the Kindle, thank you. I am, however, familiar with the Kovacs and Vassallo model of the proton, which is very similar to your notion of a PEP, where you have a Fermi scale toroidal thing with what he calls a nuclear electron.
Yes, so we are in contact with Andreas Kovacs.
Okay, and the nuclear electron, he has very interesting supporting evidence that he has observed a transition at 1551 keV that is a specific signature.
Yes, I know of that.
Again, my question to you is, we've been, we assume that it's always a proton and a proton Coulomb barrier that we have to surmount to achieve this fusion. Have you considered the possibility that there is, in fact, a neutron sneaking back where you have no Coulomb barrier, and then an ejection of this nuclear electron from the PEP? Because we spend the whole morning hearing about neutrons flying around everywhere, interacting with the structure all the time. So there is no Coulomb barrier. And in fact, it's just the ejection of that nuclear electron that Kovacs seems to observe independently of all this.
It could very well be. As I said, we are in discussions with him and his group. But I think that we called it here proton capture as being the process. That is a name, but how it exactly works, it might have to do with that actually in LENR experiments, as far as we can say, maybe the conditions are that the Coulomb barrier is gone or at least very low. And then that's what's happening.
But in this case, it would be neutron capture with no Coulomb barrier.
It could very well also be, but then you would have to have some beta minus.
Nuclear electron,
you would have to see that and to detect that.
Yeah, I'm sorry, we have to stop now because more work to be done. Okay, thank you very much again. Very interesting talk.